Hey everybody, Dr. Phil here. This is going to be a video on estimation and confidence intervals in the realm of statistics. Let's go ahead and jump right into it. So, introduction. We transition from population parameters to sample statistics. So think about parameters as sort of, you know, noteworthy things in a population, maybe like, the mean, the median, and then statistics, same thing, but just for a sample. So we use sample information to estimate the values of unknown population parameters because we can't study the whole thing. There's usually too many points. It would take too long, too expensive, etc. So we begin by studying point estimates. So given an adequate sample size, the sample mean is a normally distributed, think about like the bell curve, normally distributed random variable. And we account for sampling error by using the standard error of the sampling distribution to compute an interval estimate of a population parameter. So let's talk about a point estimate for a population mean. So a point estimate is a single value, a statistic, used to estimate a population value parameter. Okay, so the point estimate, the statistic computed from sample info that estimates a population parameter. So as an example, if we suppose the Bureau of Tourism for Barbados wants an estimate of the mean amount spent by tourists visiting that country, they randomly select 500 tourists as they depart and ask these tourists about their spending while there. The mean amount spent by the sample of 500 tourists serves as an estimate of the unknown population parameters. So again, we're not going to try to, ask every single person. That would probably, hundreds of thousands or millions of people. So let's talk about confidence intervals for a population mean. So a confidence interval, think of it like a range of values constructed from sample data so that the population parameter is likely to occur within that range at a specified probability. So the specified probability is called the level of confidence. Okay, and we estimate this, and these terms, you may or may not have seen these before, lambda, and you can just call this x bar in two situations. So the two situations are the population standard deviation, which we always use this, sigma is known, or the population standard deviation is unknown. So let's talk now about what we call the central limit theorem. So the sampling distribution of the sample mean is generally going to be normally distributed, again, with enough samples, right? So we have the mean and we have the standard deviation. Okay, so the standard deviation is basically, if we go back real quick, the standard deviation, and we just divide it by the square root, and n is the number of you know data points in our sample. And this allows us to make confidence interval statements using z-statistics, or basically probability statistics. So 95% of all confidence intervals will contain the population mean, and the z-statistic is 1.96. And 90% of all confidence intervals will contain the population mean. The z-stat for that is 1.65, so on and so forth. So the confidence level, the percentage of similarly constructed intervals that would include the parameter. So let's suppose you want the z-value for a 95% confidence interval. So we just divide that in half. So 0.95 divided by 2 is 0.750, and you can see what I highlighted here. So the probability of finding a value between 0 and 1.96 in this case would just be, we can see what I highlighted here in yellow, 0.475. So about, you could say 47.5%. So the probability of finding a value between plus or minus 1.96 would of course just be double that. So 0.95 or 95%. So here we can see obviously the normal distribution, the bell curve as we call it. You can see the 0.47s on either side of the mean, and then you can see in the tails down here we can see the 0.25 and the 0.25. All right, now the width of the interval is determined by two factors. One, the level of confidence, and two, the size of the standard error. So the standard error is affected by two values. One is, of course, the standard deviation. Two is the number of observations in the sample, right? So confidence interval with sigma known is just x bar plus or minus z, and then we just multiply that by, we could do a little bit of order of operations here, sigma over the square root of n. And then we've got our 95% confidence interval. You can see the 1.96 here that I plugged in. And then you can see the 90%, which of course is the 1.65, which of course it would be a lower number. So let's take a look at an example. The AMA, American Management Association, is studying the income of store managers in the retail industry. A random sample of 49 managers reveals a sample mean of 45,420. The standard deviation of the population is 2050. So what is a reasonable range of values for the population mean? And how do we interpret these results? So the example, in this case, x bar would be equal to 63,400, and then the standard deviation would be equal to 2050. And then you can see where I just plug my numbers into the formula. So plus or minus 1.96, and then we can just do 2050. And remember, it's n, so that's just the number of basically think about like the sample size. So in this case, 574, like you can see over here, plus or minus 574 would be the margin of error. So the interval is basically 62,826 to 63. So what we're basically saying is we expect 95% of all confidence intervals computed from random samples from the population will contain the population mean. So ideally, it'll be, there's 95% chance it'll be between those values. And then here you can just see, graphically depicted. Now, in most cases, the population standard deviation is not known because, again, it would just be too expensive to try to survey all those people. So we use the sample standard deviation, S, to estimate the population standard deviation. So we cannot use the Z distribution. So instead, we use what's called the T distribution. Okay? So there's a difference between the Z distribution and the T distribution, especially when the sample sizes are small. So you notice we got the Z distribution in the green, sort of your normal curve. You notice the T distribution is flatter. So those values, there's going to be more dispersion. There's going to be more variance in those values. The T distribution is based on the assumption that the population of interest is normal. There is a family of T distributions depending on the degrees of freedom tied to sample size. And a continuous distribution is generally mound-shaped. And we can look at the kind of shape. It's kind of mound-shaped and symmetrical. We assume the mean is 0 and that the standard deviation differs, again, depending on the degrees of freedom. So if it's flatter, more spread out than the standard normal distribution and less peaked in the middle, as we can see, as the degrees of freedom increases, the T distribution approaches the Z distribution. So as I said before, the Z distribution, this is the one that you're kind of used to doing, like a normal distribution. You can see that this is more sort of a, I think the good word for it is what they use is mound. You can tell that the observations, the data points, there's more dispersion. There's obviously there's more variance in those data points. Now the T distribution has greater spread than the Z distribution, as we just said, and the value of T for a given confidence level has to be larger than the value of Z. And again, think about why. Think about how these are shaped out. So here we can see the distribution of Z. You can see the 0.95, and then you can see here like how the 0.95 is kind of further spread out. And again, think about the more, the increased dispersion and the variance in those values. So confidence interval, if we have a sigma unknown, then it would just be x bar plus or minus t, and then just s over the square root of n, just like before. And then so the degrees of freedom, I won't get too much into like what those are in this particular video. All you need to know for this is in this one it's parametric, it's n minus 1. So we assume the population is normal. Is the population standard deviation known? Then if it's yes, we can use the Z distribution. Frankly, most times it's not going to be, so we have to use the T distribution. So as an example, a tire manufacturer wishes to investigate the tread life of its tires. So a sample of 10 tires driven 50,000 miles revealed a sample mean of 0.32 inches of tread remaining with a standard deviation of 0.09 inches. So we construct a 95% confidence interval for the population mean. Now, would it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount of tread remaining is going to be 0.3 of an inch? So in this case, we can sort of plug in our numbers here. So x bar 0.32, the standard deviation 0.09, and then the number of observations 10. So then again, remember degrees of freedom is number of observations n minus 1. So 10 minus 1 is 9. So then we're looking at 0.05 here, and then because again it's two-tailed, it could be more or less, and then we're just matching it up to the degrees of freedom, and you can see what I've put in the box here for you. So the t value is 2.262. All right. So in this example, we can plug in our 2.262. And then you can see that we spit out the margin of error, which is 0.064. So the interval is basically 0.256 up to, that would be like the low, sort of the floor, if you will, and the ceiling being 0.384. Now, if we repeated this study, about 95% of the intervals would include the population mean. Now, because 0.3 is in the interval, it's possible, not definitely, but it's possible the population mean is 0.3. But there are also lots of other values. And every time you repeated this, of course, it would be slightly different. So choosing an appropriate sample size. So the sample size is important to the standard error of a confidence interval. The sample size is not a variable, but a decision based on the margin of error, the level of confidence, and the variation or dispersion. And we generally would denote the margin of error as a sort of a capital E, as you see there. This is the amount added or subtracted from the estimate. It's the amount of error we're willing to tolerate. So, sometimes that can be more or less depending on what we're measuring. A small margin of error requires a large sample size. And of course, a larger margin of error, as a corollary to that, gives a wider confidence interval. So for a mean, E would just be equal to the z-score and then multiplied by the sigma over the square root of n. And again, remember, n is just the number of observations in the sample. Okay. And again, if looking at what you see here, you won't always have a reliable estimate. So sometimes we'll just use so if you notice here, we have the pi symbol. So notice that if he says if no reliable estimate of pi is available, then just use 0.5, and that's a pretty standard practice, especially in a two-tailed test. What that'll do is actually overstate the sample size, and if you think about it mathematically, it'll just add a bit of conservatism into your study. So as an example, a student in public administration wants to estimate the mean monthly earnings of city council members in large cities. She can tolerate a margin of error of $100 in estimating the mean. She'd prefer to report the interval estimate with a 95% level of confidence. So the student found a report by the Department of Labor that reported a standard deviation of 1,000. So what then would be the required sample size? So in this, we know that E is 100, sigma is 1,000, and then Z is 1.96. So again, just plug in your numbers, and we get 384.16. So the computed value of 380 will just be rounded up to 385. So what we're saying there is a sample size of 385 is required in order to meet the specifications and the confidence interval. As another example, or continuing that example, the student in the previous example also wants to estimate the proportion of cities that have private refuse collectors. So the student wants to estimate the population proportion with a margin of error of 0.1. So use a level of confidence of 90%, no estimate for the population proportion as is normal. So then what would be the required sample size in this scenario? So again, just plug in your numbers. E equals 0.1, Z is 1.645, and then we can just assume pi is 0.5. And again, plug in your numbers. Just literally plug in your numbers. You get 67.25. So of course we would round that up, be on the conservative side. So the student needs a random sample of 68 cities. Okay, so this is a little bit about z-scores, about plugging them in, a little bit about t-scores. Generally, if there will be times when you're not able to use z-scores, so you will kind of have to revert to t-scores. Generally, z-scores are probably better if you can use those. Unfortunately, a lot of times you can't because of there's so many unknowns in these types of studies. So you'll end up using a t. All right, thanks for watching this video, and I will see you all in a future video.